Welcome back. Happy Monday. We are going to continue this week on the simple machines. Now I'm looking at the calendar and I've been thinking about a few things that I want to happen. And I think that moving forward, after we finish the pulleys, I want to move on to something else. I don't think we need to get into all of the simple machines. I mean, we kind of have an idea about them all, and I don't want to go too in depth in this because it's harder to find the supplemental materials. All the pulley stuff is going to be questions that I'm going to post, and then you're going to go ahead and have to write on a piece of paper. And I know a lot of you guys have expressed that you like doing the work on the computer, whether it be Khan Academy or the physics classroom, and I think there's other things that would be worth your time. I know some of you may feel like all this is a waste of time, but I think that if you decide to take college, any science in college, you will find some of the things that we're going to go over in the coming weeks to be actually quite useful. So this week is going to be pulleys and pulley systems. So today we're going to start with the super basic: what is a pulley, what is tension, what is all this stuff, how does it work, and here we go. A pulley is nothing more than a rope around a wheel. In the most simplistic way possible, here's a picture of a pulley. What do pulleys do? Pulleys fundamentally change the direction or the magnitude of the force required to move an object. So if you look in the little picture on the right, the guy is pulling down and to the left, and the box moves up. The force, if he's pulling down to the left, wouldn't you assume logically that the box would also go down to the left? What the pulley does is the pulley manages to change the direction of the force, and you move things in different directions than the pull or the push, and it's in that essence that allows pulleys to be so useful. Pulleys can also provide something called mechanical advantage, and we'll get into that on Wednesday of this week. But I just want you to know that the tension in all parts of the rope must be the same at any point in time. It's not like that the F of T on this side of the pulley is bigger or smaller than the F of T here. It's the same rope. Therefore, because it's the same rope, it has to experience the same tension throughout. This is, in essence, what a pulley is all about. So, the most simplistic form of pulley that you will see on any AP Physics test is an Atwood machine, or Atwood's machine, depending on who you ask. It's got the apostrophe S. But all it is two weights hung over a pulley. If the two weights are exactly the same, they'll just stay put. But if the two weights are unequal, let's just say that M2 is greater than M1, meaning that this mass of M2 is bigger. So what that means is that gravity is the only thing that's really acting on these. Gravity pulls M2 down, but because M2 is a bigger mass, in a weird way, gravity then pulls M1 up. Because if you think about it, as M2 goes down, it's pulling the rope this way, pulling the rope this way, pulling the rope this way, and as the rope goes on the wheel, it changes the direction of the force. So obviously you knew numbers were coming. I have a question. Well, two questions. What is the tension of the rope? So here is a brand new equation that you've never seen. Force of tension equals mg minus ma. Now, there are two things I want you to know about this equation. This equation applies only for freely hanging objects. So we could not use this last week when we had the boxes on the table. It applies only to freely hanging objects. So this would not apply to the rope and the boxes on the table because those are not freely hanging, they're touching the table. The other thing you need to know about this equation, this tension equation, is that applies to one mass at a time. So you're not going to combine the masses in this equation. Applies to one mass at a time. Okay, so this is going to be a lot, so let's get ready. How do we figure the acceleration of this equation first? Well, let's draw the free body diagram. Well, I know that gravity is pulling down on the 5 kilogram crate 49 newtons. 5 times negative 9.8 is negative 49, or 49 down. So, what is gravity pulling on the 3 kilogram crate? 3 times negative 9.8, good. 29.4. Awesome. So that's what gravity's pulling. Gravity's pulling down those 2 boxes. But since they're attached to this rope, there's going to put some tension in the rope. So let's look at the 5 kilogram box. If the 5 kilogram box is being pulled down 49, it's being pulled down 49 on the whole rope through the top and then over. And then technically, we could say that on this side, it's being pulled up 49. And then the same thing could apply for this, for the 29.4. It's being pulled down 29.4, and it's pulling it down through the whole rope, and it goes to the pulley. And that means the down of 29.4 is now an up of 29.4. So either way you look at it, you can get the same net force. What's the net force here? The net force is going to be 49 minus 29.4, or in this case, should be 19.6. Hold on, sorry. Yeah, I'm sorry. It is 19.6, excuse me. 19.6 newtons. And just like before, the mass, just like we did last week, is going to be both masses together. You add the masses because they move as one. So both of those masses are going to experience that same net force. The 5 is experiencing that force down. The 3 is experiencing it up. So the acceleration is going to be the 19.6 divided by 8, which you get 2.45. Now my question is this acceleration up or down? Well, the answer is, it depends. It depends, I'm going to erase some of the stuff here. It depends on which side that you're talking about. Are you talking about the 3? Well, if we're talking about the 3, then the acceleration is going up. If we're talking about the 5, then the acceleration is going down. So it depends on the side that you pick. So here's how we do it. Now that we have that all done, I'm going to erase the free body diagram. All right? Erase, 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 erase all this. And this is what we're going to do. We are going to look at this equation, this brand new equation that we have never used before, that's written F of t equals mg minus ma. And we're going to see how it's going to work. I want to find the tension in the rope. I find the acceleration from the free body diagrams and subtracting the gravities. That's how I got the net force divided by all the masses, and I get this. Bam. Okay. Now, to use this F of t equation, have we met the 2 conditions above? Well, both of these are freely hanging in the air, so we can use this equation. And it only applies to one mass at a time. So let's go ahead and start with the 5 kilogram mass. F of t equals 5 times negative 9.8, that's gravity, can't forget the negative, minus the mass, which is 5, because it only applies to one mass at a time, so we're not adding them for this equation. One mass at a time, we're not adding them. And is the 5 kilogram accelerating up or down? Down. The one with more mass is accelerating down. So it's going to experience an acceleration of negative 2.45. So all we do is we just type that in the calculator. We just type that in the calculator. 5 times negative 9.8 minus 5 times negative 2.45. Excellent. The tension we get is negative 36.75. Awesome. Newtons. Now wait a minute, Bizzuto. What if, just what if I didn't choose that side? What if I decided to find the tension by looking at the 3 kilogram instead of the 5? Let's find out. Well, it's mg3 times negative 9.8 minus 3, but this time is the acceleration up or down? Is the 3 kilogram weight accelerating up or down? The 3 kilogram rate is accelerating up because this is what's happening. This is the motion. That's why the 5 was going down and the 3 was going up. It was pulled through the pulley. So this is going to be positive 2.45. Oh, fascinating. What if I type that in the calculator? Well, typing that in, wait a minute, no way. Negative 36.75 newtons. It does not matter the side that you pick. You can pick either side to get the tension. So the whole point is the tension is the same in both sides of the rope. And this makes sense because it's the same rope. It's not like if it's just the same rope and the only things are pulling at the ends, the tension needs to be equal throughout the whole of the rope. So it doesn't matter whether I look at the left side or the right side, I'm going to get the same tension. The tension in the rope is negative 36.75. Bizzuto, what does the negative mean in terms of tension? Well, negatives get a little screwy with tension because it's pulling both up and down at the same time. But essentially it just means the whole system is going to be moving down, which it kind of does make sense. The 5 is pushing it downward. That is the dominant direction. Okay. Look at that. That's it. That's how you do an Atwood's machine. I can guarantee that no AP Physics student can finish an AP Physics class without seeing that. So you have now joined the ranks of all AP Physics students. Now you are in your knowledge of an Atwood's machine. That's all it is. You find the acceleration, and then you use this equation. Now, another situation that we sometimes look at is a pulley on a table. These are very, very common problems, but let's think about it conceptually here. This mass right here is getting pulled down by gravity. This mass is getting pulled by gravity. But this mass has a normal force. So let me just label these. F of G. F of G. It's going to be different because they have different masses. This is going to have a normal force. F of N. The friction will, of course, oppose the motion. And remember, I said that the force of tension is going to be the same. The force of tension is being pulled evenly in the rope. The force of tension is pulling the same number on each of those boxes. So if we could figure out the force of tension at one spot, we could find the force of tension in the other spot. So this is another example of a pulley, and we are going to look at this with numbers now. Never, ever, ever forget how to draw a free body diagram. In this case, we've got gravity pulling down 29.4. That's gravity. 29.4 newtons. Here, we have gravity pulling down, hold on 1 second, sorry. There it is. 78.4 newtons. So we're just drawing free body diagrams. That's it. We just have to recognize the forces here. It's going to look exactly like the other situation we just looked at. So if it's being pulled down 78.4, it's being pulled up 78.4, by the normal force. And do you remember how to get the force of friction? Well, if you don't, I'll quickly remind you. Force of friction equals mu F of n. We know this is accelerating. I mean, we don't know. I could make you go ahead and figure that out, but I don't think that's necessary right now. So I'll just tell you it's accelerating. I'm telling you it's accelerating. So we can go the 0.15 times the normal force of 78.4 is 11.76. Awesome. So what's the tension? How do we get the tension? Ooh, I don't know. Well, oh, I've got it. If B is pulling down 29.4, okay? If B is pulling down 29.4, we can kind of assume that A and B, this is getting pulled, oh, sorry, this is getting pulled 29.4 as well. So, because it's transferring through the rope, it's transferring through the rope. So, what is the net force acting on this object? So the net force is going to be the 29.4 minus the 11.76, the friction. Look at the free body diagram. So the net force is 17.64. Nice. Nice. That's the net force that's acting on this. So we need to get the acceleration. To get the acceleration, we have to add the masses. We have to add the masses. The masses are 8 and 3, which is 11. So the acceleration is net force divided by mass, so 17.64 divided by 11. So the acceleration, we'll just say for simplicity, is 1.6 meters per second squared. So what we're saying is that box B is accelerating down 1.6 meters per second squared. Box A is accelerating right 1.6 meters per second squared. Now, here's the question. Just because box B is pulling on the rope 29.4 doesn't mean that's equal to the tension in the rope. We still don't know what the tension of the rope is, but we can now solve for it using this equation. F of t equals mg minus ma. I still want that tension. We haven't figured it out yet. So this is what we do. We are going to go ahead and use from the perspective of mass B. We can't use mass A because it's not freely hanging. So we're going to use from the perspective of mass B, and it always has to be the freely hanging mass. 3 times negative 9.8 minus 3, and the acceleration in this case is going to be down, so negative 1.6. Just type that in your calculator. So we have a tension of F of t of negative 24.6 newtons. Now, how can we go ahead and check to see if that's right? We can look at each one individually. We can look at each box individually. We know they move together. But let's just pretend, let's just pretend that this was 24.6 newtons, and now this was 24.6 newtons, because this is actually what is getting pulled. Let's think about it. Let's think about this for just 1 second. Let's look at box B. 29.4 minus 24.6 equals 4.8. So the net force for B is 4.8. What is 4.8 divided by 3? The mass? When I do that, the mass is 3. I have an acceleration of 1.6. We already knew that. It's working. It should check out. When you look at the system individually, the tension is actually the force that goes in the free body diagram. So I had, over here, I had the 29.4. That's not the number that should have gone there. That was there just to illustrate where the force was coming. It was really this 29 minus this 11 to get the net force. But these other forces, this tension force, is really still here. So now let's look at box A. To get the net force, it's going to be 24.6 minus 11.76. So I get a net force of 12.84. When I divide that by a mass of 8, just take a guess what that's going to equal. And that's exactly what it should. It's just a way of checking your work. So there's a lot of stuff going on here, but if you really understand the free body diagrams and the tension equation, it should make sense. Watch this through several times because your homework will require you to do a question like this. So that's it. These are the basic facts of pulleys. We haven't gotten to mechanical advantage. That will happen on Wednesday. I just want you to know that because we're not in class, we are not going to be able to do the problems of a pulley being pulled down an inclined plane. I really do enjoy those problems. You have all the inclined plane forces, gravity, pulley, you mix them all up. But don't worry, we're not going to do that this year. In college, when you take physics, you will see that, but not here. So yeah, we have two masses hanging on a rope is a pulley, in essence. What is the name of the picture here? This is called the Atwood machine. And if you don't believe me that an Atwood machine is real, Google it. On Wednesday, we'll get into how elevators work and how you can use pulleys to lift heavy weights with ease. But until then, I wish you luck, and please do not hesitate to reach out if you need any help. Again, I am here. Join the office hours or just shoot me an email. We'll figure this out. Be well.